Today's topic is optimizing petrophysics to solve complex mineralogy in conventional reservoir. Optimizing petrophysics feature in Geolog is known as Multimin. Geolog is our formation evaluation software in Emerson ENP software portfolio. So today's agenda includes, like, in the introduction part, I will talk about deterministic analysis. This will help to know the difference between deterministic and the probabilistic method, which will be followed by the optimizing or the probabilistic method theory. Then I will discuss about the workflow of how to use the optimizing method in the Geolog and how you can generate the results. Then we'll discuss about some of the new features. In last couple of versions in Geolog, we have added some new features. One of them is the probabilistic model switching, and then we have probabilistic method or the Monte Carlo uncertainty analysis in Multimin. So I will discuss about that. Then I will do a short demo. In this demo, it consists of two parts. In the first part, I will show how to generate a model and how to run this model and generate a result. Then we'll just show the new features. Finally, the conclusion. And if there is any question, I will try to address that as well. So when we talk about petrophysical analysis, there are two kinds of petrophysical analysis. One is the conventional deterministic method, and second is the probabilistic or the optimizing method. In a deterministic method, petrophysicists calculate the reservoir properties in a series of steps. So the first step is usually the V shale or the shale volume estimation. The shale volume can be estimated from a single log or a combination of log. For example, a V shale can be computed from gamma ray. Once the shale volume is computed, the next step is to calculate the porosity. Again, porosity can be calculated from nuclear logs or even from a single log. Even if you have acoustic log, we can use to calculate porosity. So for effective porosity estimation, it needs input from the previous step, which is the shale volume. So once the porosity is calculated, the next step is to calculate the saturation. So saturation can be calculated from various standard water saturation equation. So for water saturation calculation also, it needs input from the previous steps. So as you can see, there is a backward dependency on the variables. Also, it lacks the multidimensional interaction between various log measurements. There are some iterative deterministic methods available to calculate or to use the multidimensional interaction, but which is not commonly used in the industry. So in 1980, Mayer and Sibit formalized a new approach to petrophysical analysis. So they focused on the response of each wireline logging tool in the environment which is logged, and then they have set up a response equation for each logging tool measurement in terms of volume of minerals and fluid in that particular formation. So if you look at this slide, you can see a typical logging tool measurement. So when I say a logging tool measurement, it is the response from the formation. So formation means the response from minerals and fluids in the formation. Also, this logging tool measurement will be depend on the tool physics. So if I'm having a acoustic tool or a nuclear log, so the physics of the tool is included. So if you use a response equation, so it is possible to generate a pseudo measured logs using the response equation. So you can see in this response equation, the parameters are the volume of minerals and fluids in the formation, also the properties of each minerals and fluids. So usually based upon geological knowledge or from a cross plot, it is possible to know the type of minerals, and from a mud gas data or a mud cutting, we may be able to get to know the type of fluids. So if we know the type of minerals and fluids, but what we don't know is the exact amount of minerals and fluid in the formation. So once we know the type of minerals and fluid, it is possible to use the response equation for any of the logging tool, and in the response equation, we can provide the parameters which are the properties of minerals and fluid, and it is possible to generate a pseudo log. So once I have a pseudo log, so we can compare with respect to the measurement. If there is a good match between the modeled and measured log, we can say we have calculated the mineral and fluid volume correctly. If there is a mismatch, it is possible to adjust the mineral volume or change the properties of mineral and try to get a good match between modeled and measured logs. When I say good match between modeled and measured log, we can say we have come to the most probable solution. So in a petrophysical model, these are the theory of the probabilistic method. In this probabilistic method, it consists of different components. One of them is the petrophysical model. So assume in a rock which have two minerals, quartz, feldspar, and there are two fluids, oil and water. So if I use a response equation, you can see this is the response equation of density log, which is a linear equation. So I can say a model density is a function of density of oil in the formation times the volume of oil in the formation, which can be added to density of water times volume of free water, which again can added to individual minerals and the property, in this case the density of minerals. So once if you use this response equation, it is possible to generate a pseudo density log. So once we have a pseudo density log, we can compare with respect to the measured data. So once we have both modeled and measured data, we can calculate the difference. So if the difference, which is the error, is close to zero, we can say I have come to, or I have calculated the mineral volume correctly. But you can see this is a single equation, and in this single equation which have four unknowns. So it is possible to have infinite solution. So in order to get a determined solution, we need to have a minimum of four response equation. So what I do is like in this particular slide, along with the density, I have added three more response equation. One is for the gamma ray, second is the neutron, and the third is the conductivity. In Geolog, for probabilistic or optimizing method, we don't use resistivity, we use conductivity, which is the reciprocal of resistivity. So assume at a depth of 1000 feet, you can see the measured values of gamma ray, neutron, density, and conductivity log. So using the response equation of each of the logs, it is possible to calculate a model log. So once we have a model log, so we can calculate the difference between each of the measured and model logs. So we can see the difference, which is the error. As we know, in order to get a determined solution, we need to combine all these response equation, and that means we need to combine all the error. And when the error is close to minimum or close to zero, we say we have calculated or we have estimated the mineral volume accurately. But you can see each of these logging tool measurement, let's say for density, which is having a unit of GAPI, and for example, for neutron, it is volume by volume. So each of these tools have a different range of units and numerical values. So if you combine this error, it's not going to have equal weightage in the error minimization. So what we did in a multimin is we have introduced a parameter which is known as the uncertainty value. So this uncertainty value is used so that each of the logging tool response equations have equal weightage in the error minimization. So if I look to the density equation again, so you can see the error is the difference between model and the measured log. So this uncertainty value is introduced in the denominator so that the weightage of, like if I use a density, it will have equal weightage compared to other logs. So what we can do is, so this single error approach for like density, we can expand to a full least square implementation by summing the error of each of the logging tool prediction. So what we can do is we can calculate the difference and the error, and then we can use the uncertainty value so that all the logs will be in common base. Then we can use this full least square implementation. This is known as incoherence function. So the ultimate aim of like modeling is like we need to have a minimum incoherence function. That means a good match between the modeled and the measured logs. So when we do this petrophysical model, it is important to incorporate geological knowledge in the optimization. Otherwise, it is possible to have negative volumes as well. So in order to do that, we have introduced two parameters. One is the bounds. Bound will be applied on a single component volume, and the second is the constraints. Constraints put restriction between several components. So in Geolog, we have some of the default bounds. For example, the sum of volume of minerals, it can be like a, sorry, not the sum, it is the individual mineral volume. It can be between 0 to 1. For the fluids, it can be between 0 to zero point 0.5 only, even for flushed and the unflushed zone fluids. Regarding the constraints, you can see the unity constraint, which means the sum of all the volumes, including minerals and fluid, it should be 1. Second is the equivalent fluid constraint. So summation of fluids in the unflushed zone and the flushed zone fluid should be same. So you have seen like the petrophysical model, which where we have take the minerals based upon the geological knowledge, and then we combine like response equations. Response equation for each logging tool is most of the time like the response equation used in Geolog is of linear form. So the example you can see for the density, this is a linear equation. For all other like a linear form equation, this is the general equation used. That means like a modeled tool response is a function of volume of individual minerals or fluids to the property of that particular minerals or fluids. But there are some of the response equations which are non-linear. For example, thermal neutron. The response of thermal neutron device are not linear with respect to volume of different minerals and fluid present. This you can see in the interpretation chart of major logging service companies. And even for the value of parts, for a low porosity sandstone, it is between negative 0.01 to negative 0.02, but for a high porosity sandstone, the matrix value is as low as negative 0.05. Another nonlinear response equation is for the saturation calculation. So you can see for dual water equation. So in Geolog, if this you can see the standard equation in the slide. So this standard equation is rewritten in terms of fluid terms. So you can see the standard equation is written in terms of volume of bound water and volume of free water. So in these response equations, we have to incorporate the parameters. So parameter means the individual properties of minerals and fluids. For the default value of minerals are provided for the common tool types in Geolog Multimin model. Multimin user can accept it as a starting point. Regarding the clay properties, which includes both dry and wet clay, during the optimization, Multimin calculates volume of wet clay and then it is broken down to volume of each dry clay. The clay bound water is the sum of the bound water for individual clay minerals. For fluid properties, the fluid response are mostly dependent upon temperature, pressure, and salinity. So this is calculated internally only, and sometimes if user want to give his own value, we can override it also. So critical parameter, another critical parameter in is the equation uncertainty. The mathematical objective of an equation uncertainty is to provide equal weightage to all the response equations. However, like this is it is important to give consideration to three phenomena when you adjust this uncertainty value, and this is important when you are building a good multi-min model. So one of them is the each of the response equation which have a error of measurement or precision. So each logging tool have like a different error of measurement which affects the repeatability. Another is like individual logging tools have a different vertical resolution. The third is like for each measurement, like in the same sedimentary environment, it can give a range of values. So when we give this uncertainty value, these three parameters or these three factors to be considered. So we have talked about the petrophysical model, and then we select the response equation. In the response equation, we give the parameters for minerals and fluid. The final stage of this probabilistic analysis or the optimizing method is to minimize the incoherence function. So for all linear response equation, the minimization of incoherence function is achieved using an algorithm described by Goldfarb-Idani. For nonlinear response equation, the first step is to linearize the nonlinear equation, and in the second stage, it involves a complex iterative consideration of sensitivity of incoherence function for each of the volume components, and it uses a nonlinear engine to solve. The engine used by Multimin was obtained from UK Atomic Energy Association and is written by Powell. So since like in this mathematical model, usually user doesn't have any interference. So when a petrophysicist or an analyst build a multi-min model and when we run it, it will run automatically in the background. So when we talk about this mathematical model, there are some of the QC parameters which is important. One is like when we build a model, we want to know how good is the model. So this is given by a option called condition number or a resolution number. So which will give like how good your model is. So if the value is less, we can say it's a good model. The second is like when we run the model, so you want to say how good how good is the quality of model in terms of mathematics. Obviously, we can check the result and see, okay, is it like the calculation is giving exact volume of minerals I'm expecting, it is possible. But in mathematical terms, we get a quality curve. The quality curve is derived from the incoherence function. If the quality is close to 1 or below 1, it says there is a good match between measured and the model logs. Another quality indicator is N1. It doesn't have any relation to model QC or the result QC. So what it says is how many iterations to solve the model. So usually, like if you use a nonlinear equation, you will see a spike. So it may need like more iteration to solve the model. So in summary, the main part of Multimin model is the petrophysical model, where we take the volume of minerals and fluids. Then we will set up the response equation. So it can be linear or non-linear. And in the response equation, we input the parameters. So it depends on the properties of individual minerals. Finally, the mathematical model, which is used to solve or the minimize the incoherence function. So now I'm coming to the interpretation model, like as we do an analysis. So usually what an interpreter is having is a tools. Tools means the logs or the measurements. And what we need to calculate is the volume. So based on the geological knowledge, we may know the type of minerals and fluids I'm expecting. And the third important option or the parameter is the properties of minerals and the fluids. So these three are the main pillars of a multi-min model. So if we know any of the two, it is possible to calculate the third one. So you can see T, which is the tool or the logging tool response, is a function of volume of minerals to the properties of individual minerals and fluids. In a typical multimin, what we do is we are calculating the volume by using the properties of minerals and also the logging tool response. So there it is also possible, like if we have a volume, so from an XRD data, if we have logs, we can calculate the parameters also. And this is known as NIMPL in Geolog. That means like a numerical inverse method by linear equation. The third option is synthetic log generation. So if we know the volumes and parameters, it is possible to calculate synthetic logs. The good example I can say is like sonic log generation. For example, if we have an old well where we don't have an acoustic log, so if we have a multimin model, we can use the multimin model, and in that volumes we can give the parameters for the individual minerals. So acoustic log response, it is possible to generate a synthetic log also, or synthetic sonic log. So these all are about the theory parts. So now I'm going to discuss about the multimin workflow. So as in any petrophysical interpretation, the first step is the data preparation. So where we will do the QC and condition the logs. Once we have a condition log, the next step in multimin is to run a or calculate the downhole mud properties. The feature in Geolog is known as precalc. So in precalc, what we does is we calculate a continuous temperature pressure curve. If we are using a water-based mud, we generate a resistivity of mud curve. This is at this stage we will calculate the conductivity for using in the multimin model. So once we done the precalc, the next step is the building the multi-min model. So this is where we select the logs, which are the known measurements, and we select the unknowns. These are the volumes we need to compute, and then we build the model and we provide the parameters for individual minerals and fluids. So once we build the model, we will run and view the results. So while viewing the results, we can do the mathematical QC and we can check how our calculation is done. Once we have like a result, if we have some hard data like XRD or core, we can compare or calibrate the result. And if the results are not good, it is possible to refine the model. So you can go back to the multi-min model, you can change parameter and you can refine the multi-min model. So that's about the multi-min workflow. So you can see in this slide, this is the multimin results with the QC plot. The first track shows the volumes computed. So we can see the volume of minerals and fluids. Third and fourth tracks, in the third track, you can see porosity, and the fourth track shows the saturation. So you need to remember, like multimin is calculating the volume of minerals and fluid. Porosity and saturation is a post-processing result from multimin. Along with this result, we can have the QC plots, the analysis quality, which shows the mathematical model QC, which includes condition number, quality, and end fund. So you can see some spike in end fund. So this is model is generated using a nonlinear equation. That's why it's showing the spikes. It takes more iteration to solve the model. And the last 5 tracks shows the comparison between measured and model logs. So the red color curves are the predicted or model logs, and the black color curves are the measured logs. So you can see there is a good match between measured and model logs. So now I'm going to talk about the new features. So this Multimin is in Geolog for quite a long time, and in the last couple of versions we have added some new features in Multimin. One of them is the probabilistic model switching, and second is the Multimin uncertainty analysis. So the in Multimin, it is possible to switch between a primary model and up to 10 secondary model. So assume like if I'm working in a clastic reservoir and if there is some calcareous streaks, it was possible to write an expression saying, okay, I have a primary or model, which is like the clastic model, but where if there is an area where there is calcareous streak, let's say like density is greater than 2.6, run the calcite model. So it was possible in previous version also. So what it does in probabilistic model, which is incorporated in Geolog 19, what we can do is we can mix the model. So for example, if you look at this particular cartoon, so you can see in the x-axis is the gamma ray, y-axis is the probability of shale. So in this particular case, what I need is like below 60 gamma ray, I want to run the model one. Let's say call it the sand model, and above 100 gamma ray, I need to run the shale model. But what I need is in between 60 to 100, I need to mix the model. So in Geolog, we use like a point slope equation to mix the model. So if I am close to 60, I will have more proportion of the sand model. And if I'm close to 100, I will have more proportion of the shale model. So this is how the probabilistic model mixing is done in Geolog. So if you look at I will show that in the demo part also how we do the mixing from different models. The second new feature is the multi-mean uncertainty. So for a reservoir modeler or a geomodeler, in order to calculate the reservoir volume, they need a reliable estimate of porosity, water saturation, net to gross rock volume, and recovery factor. So you can see the formula to calculate the reserve volume. Among these like 6 parameters, the 3 parameters are coming from petrophysics. So if there is any uncertainty in these values, it is going to have huge impact on the reservoir volume. So in order to do that, we need to have like a reliable estimate. Also, we need to know the range of values, what could be the best and low case or high case for individual, like let's say for porosity or saturation. This uncertainty feature has been added in Geolog from Geolog 7, which was for like deterministic uncertainty analysis. Our R&D has done extensive work on to incorporate this uncertainty analysis in Multimin. So this feature was added to Multimin in Geolog 8. And in this uncertainty analysis, it is possible to run uncertainty on any input parameters and the input log. Also, you will be able to get the uncertainty outputs on any of the multimin outputs. The outputs are usually an array curves. Once we have the array curves, it is possible to calculate the statistics. So for example, if you look at this slide, you can see the porosity and saturation distribution from multi-min uncertainty analysis. And in the last track, so from this array histogram for the saturation distribution, I have generated a statistic saying like what is my P10, P50 and P90 values. So this is a good feature like where you can run uncertainty within the multi-min model. So the next step is I'm going to show you the demo. As I mentioned, the demo have 2 parts. One is how to run generate a simple multi-min model results. The second part is to show how to use the new features. So if you look at these slides, this is a Geolog typical well window. So this is a text view for one particular well. I have some basic data available for this well. So in Multimin, so we need to do the QC. So I just generated this result for the demo. If I go to the work area in Petrophysics menu, you can see the Multimin model and the Multimin launcher. this is where the Multimin model is the option where we build the model, and once we have the model, we use the Multimin launcher to run the model. Also, if you go to this processing menu in the Petrophysics, you will be able to access the Multimin. So here also you can use to select the Multimin model. So what I did for demo is like I have created a custom workflow, and this is one of the nice feature in Geolog where like depending upon the area you can create your own custom workflow so that you can make your analysis easy and you can save this workflow and you can use it for like a later part also. So as I mentioned during the workflow part, the first stage in Multimin, the workflow is to have a QC and the data preparation part. So for example, I'm not going to do the data preparation as it takes more time. So I have a composite plot where it will show the data available. So you can see I have gamma ray, resistivity and nuclear logs available for this well. In this well, I also have a acoustic log. But what I will do is I'm not going to use that in the model because I want to show how we can predict the synthetic sonic using the Multimin model. So once we have the condition data and you can see in the slide, assume it's in the composite plot, the next step is to calculate the downhole mud properties. So in order to do that, we use precalc. So once I launch this module, first I can define the input and output set. And the next step is in order to calculate a temperature and pressure channel. So we have various options. We can use a top log or bottom log interval. This is the case I used here. If you have a gradient or a tool measurement, you can use that also. Once you select the option, next is you can select which which mud system you are using. If it's a water base and oil base, and if you can provide the mud density also. So here it is a water based mud. So I have given the mud properties there. And if I go down to the input logs, so you can see there are various options one of them is the true formation resistivity and flush zone. So if I give my resistivity value, it will invert and calculate the conductivity channel, which you can see. And even like if you have PEF curve, because in Multimin we cannot use PEF, so it will using the density, it will calculate the photoelectric absorption coefficient. So you can see the temperature channel, temperature and the hydrostatic pressure channel, and the mud properties are calculated here. So once I run this module, and if I go to the text view, so you can see here the results calculated. So these are like a continuous channel. So even if you run a pre-calc, if you go to there is a layout by default it opens. So you will see the mud properties and the temperature pressure calculated at each depth. So once we done the pre-calc analysis, the next step is to build the Multimin model. So you can select a Multimin model from here. So for the demo purpose, I have some Multimin models already ready. So I'm going to open one of the Multimin model. So if I open this Multimin model, or if you're creating a new Multimin model, the first step is to select the knowns. Knowns are the response equation or the wireline logging tool measurements available with us. So that we can do using the equations tab. If I select the equation tabs, you will see like four various box options. So one of them is the wireline and LWD. So if you have a continuous wireline and LWD logging data, you can use that. So you can see the basic log options available here. Also, if you want to incorporate advanced logs like NMR, ECS, you can use that also. If you have a new log which is not defined, you can use the user defined option. Other than the continuous log, sometimes you may have like a core data which is a point data. You can use core XRD or a petrographic data into the model. In this case, I have a continuous wireline data, so I have selected density, neutron, gamma ray, conductivity. I mentioned I'm not going to use sonic, but we need to do is in order to generate the synthetic, we need to select the logs which you are going to generate. So I selected the sonic log here. So once we select the knowns, the next is to select the unknowns. These are the volumes we want to calculate. So you can select the volume tab. So once you select the volume tab, you will see the minerals and the fluid option. In the minerals option, we can select the different minerals available. So for example, you can see quartz, orthoclase, calcite, those options are there. If somebody is working in unconventional reservoir, they want to model corrosion, so you have the option to select corrosion, and even pyrite is also there. And if there is any special mineral you want to use, you can select that also. Those all options are available in the volume tab. Now coming to the fluid part, when we say in the fluid part, we need to split into two, one for the flushed and the unflushed zone. So for both flushed and the unflushed zone, we have the hydrocarbon options like oil, gas. Both options are available. Then we have bound water options, irreducible for the connate water, and free water we can select. The special fluid option is for barite mud. Isolated option is for the works. Parallel is for the fracture porosity. And if you are using an oil-based mud system, you can use the OBM filtrate option. So in this particular example case, what I am going to use is a quartz, and I am going to use a wet clay. So because I selected the wet clay, I'm not going to use the bound water. So once we select the minerals and fluids, the next step is to select the response equation. So the response equation we can select from the method tab. So once you select the method tabs, you see the equations, all the equations available. For example, density is a linear equations. So here, like for neutron, it's linear equation is there. But if you know the type of logging tools you are using, you can select that. So almost all the tool options are available. So you can select the logging tool which you want to use. Same way for like sonic, you will see Wiley equation. Also we have the Raymond Hunt Gardner equation also. So here, like you can see, all the logs or the logging tool response I selected is shown here. So now coming to this saturation equation, so I'm using Indonesian here, but we have the options like dual water, Waxman Smith, all the options are available. So once we select the response equation, so here I just want to mention, I told like I'm not going to use sonic log in the model. So you have the option, if you go to the active log, I put it no. That means the sonic log I'm not going to use in the Multimin model. But I need to select these logs in order to generate the synthetic sonic data. So once we do this, select this response equation, and next is to select the parameters. So one of the important is the uncertainty parameters. So we have given the default values. If you use the default values, all the logging tool response equations have equal importance in the modeling. So if you want to, let's say, for example, I'm working in an area where there is some washout happen, so I don't rely on density, you can increase the uncertainty value. That means this log will be used in the model, but the importance will be less. And even instead of using a single value, it is possible to use a log option also. In Geolog, if you go to the Multimin, there is an option where you can calculate a continuous log uncertainty for each logging tool. It is based upon the depth and repeatability uncertainty along with the environmental correction. So you can generate a continuous uncertainty channel which you can use in the model. So here I'm going to use the default value. Once another thing, like if you depending upon the saturation equation, you can define the AMN value. So once I select the uncertainty response equation, next is I want to give the individual minerals property. So this we can give in the formulation tab. So you can see the density value for quartz and wet clay is given there. Also, I have mentioned like the constraints in order to have a geological meaning. You will see the default volume constraints and the bound volume here, the volume bounds here. So for example, like volume bound for quartz is 0 to 1, so I can have like a minimum of 0 and I can have a maximum of quartz of 100%. That is the one value is there. Even like we is depending upon the minerals, we can define the mineral properties like the density of quartz and the wet clay using the model. Since I'm using an Indonesian equation, you can provide the resistivity of shale also. So now, so far, like we have discussed about the properties of the minerals. Now coming to the fluid properties, if you look, you will see it's all grayed out. The fluid properties are calculated based upon the values given in the fluid property tab. So if you give a value here based upon these properties, it will calculate the, let's say for the density of flushed zone gas or unventilated zone gas, these all are calculated. So now in like these all is needed if you want to run a simple multimin model. In the last, like Geolog 8 onwards, we have given an option called extra output logs. So what it does is, let's say if you remember, I mentioned I selected sonic, but I'm not going to use the model sonic log in my model. So you see, if you look at the synthetic logs, you will see a synthetic log option. This is the synthetic log which is generated. Also, if you want to get a hydrocarbon corrected logs, if you go to the method tabs, you will see the output wet options. So if you toggle on that, so if you're working in a hydrocarbon interval and you want to get a hydrocarbon corrected density based upon the fluid properties we define, you can select that, it will be output. Also, like in the extra output logs, you will see the normalized mineral volume. So the multimin volume we are calculating for the rock volume, but if you are doing a rock physics analysis, we may need to have the normalized volume for calculating this mineral or the matrix properties, so which you can you have the option to toggle on. So once you toggle on this, the normalized volume for matrix portion is also calculated. So once we build the model, we can check the status of the model. So you can see the condition number also. If you click on feedback, it will show you how good your model is. This is the condition number. Here you can see it's a 2.4 is the value. Lower the condition number, I have the good model. So once we build the model, next step is to run the model. I can go to the run analysis tab, and in the run analysis tab, I can select my input and output set. And in the run analysis tab, you will see two options. One is the module parameters and the interval parameters. So the purpose of module parameter is like if you are using like a point data set like XRD, so it's a point data, you can define which set is there. In addition to that, if you want to compare your multimin volume with respect to XRD, so you need to if you want to convert volume to weight by weight, we can do that also. Or if you want to have a continuous fluid response log, let's say density of fluids, we can generate that. Or for each of the outputs, multimin outputs, we can calculate the uncertainty. These all options are possible in the module parameter tab. But for running a multimin model, we need to provide only the parameters in the interval parameter option. So in order to run this, I already have a model built. So I restore that model. So if you look into the interval parameter, you can see I have selected shale 1 model. I've defined like temperature and the mud filtrate since it's a water-based mud. And now we need to give the RW and the temperature, the resistivity of water and the temperature, and also need to provide the hydrocarbon properties, if it's an oil API and the gas specific gravity value. So once you define these inputs, you can run this model. Once we run the model, you can view the results. If I go to this Multimin QC, as you can see, the first track which I selected, you will see the volumes and the mineral volumes are calculated. Also the fluid volumes. The third track will show the porosity, which is a summation of the fluids, and the fourth track shows the saturation. Along with this output result, you will see the QC plot, which will show the quality indicator. So this will say at each step how good the modeled and the measured logs. So if you look in the last 5 tracks, we can see the red color is the predicted log or the model log, and the black is the measured log. So you can see a good match also. And even like since it's a non-linear equation, you can see some data spikes in the end form. The model, the condition number you have seen already, it was like 2.4. You can see there is a good quality also. So this is how we run a multimin model and generate a result. So now I'm going to talk about how to mix the model. So what I will do is like I go to my launcher. I already have a shale 2 model. So I will restore, and the shale 2 model I will write into a different set. So you can see like the previous output was in shale 1 set. Now this output is in a wire shale 2 set. So if I run this model and if I open this particular layout, if I scroll down, you can see this is the output from model 1, which will have like a clay type 1 and quartz, and I have another model called clay type 2 and the quartz model. So you can see these two models. Now, in order to mix the model, so if you want to mix the model, you can go to the launcher. So in the launcher, this is the first selection expression is where in previous version also we write the expressions like if the density is greater than 2.6, run the secondary model. Same way in this expression, we can write the equation for the point slope equation. For example, like if I restore, I have the model mix equation. So if you look at this in the first selection expression, you can see I have written a point slope equation, which is simply a shale volume from gamma ray equation only. What I meant here is like below 50 gamma ray, use the primary model, and above 90, use the second model. In between, mix the model based upon the proportion. Instead of this, if you want to physically write, let's say I want to mix the model with zero point 0.5, so if you want to mix 50% of shale 1 and shale 2, you can do that also. So when you mix, you can see the probabilistic model mode. So I have given here the average. So we have the option to use mix or minimum or maximum of the first model. So that option is also available. So here I'm just going to choose the condition. So I go back to the previous condition. So I will run this model. So if I go to the model mix, you will see the mix model result, and also you will get the probability also. So probability means, for example, if I go look at this probability in between 305 to 3075, so you can see there are areas where the gamma ray is less than 50. It is using the model 1. So if I look in between 3075 to 3100, that's 3100 depth, you can see in some areas my gamma ray is greater than 90. So it is using only the model second. So you know, like at each depth, how the mixing is happened. Also, if you look at the last track, you can see it is from the multimin volume, it is calculated the synthetic sonic log. So you can see compared to the measured log, there is a good match between both model and the measured log. This is where so if you use like multimin model, you can mix the model also. Even you can generate synthetic logs. Even you can generate the hydrocarbon corrected log also. So now what I'm going to show you is discuss is the uncertainty analysis. So in the multimin launcher, there is another tab called Monte Carlo configuration. So if you select this Monte Carlo configuration, it's grayed out only. So below, if you look below the launcher, you will see a Monte Carlo box. You need to select the Monte Carlo button. So once you select the Monte Carlo button, you can see all the input parameters, which includes the parameters are the and the logs also. You can see CTCXO is the log, temperature, pressure is there. But if you look KCl mud, oil API, these are the values we are given in the Multimin launcher. So we can select all the options we'll be able to see, and you will see the output logs also. Whatever the outputs generated from the Multimin, you can see all of them. So here, like what I'm going to do is I'm just going to select density and RW value. I want to see the effect on effective porosity and saturation. So I will select density. So when you select density, you can see which probability density distribution you want to select. So we have the options to use normal, uniform, triangular, even log of all these three features are available. I select like a normal only. So once you select normal, so you can define how you want to shift. You want to shift based upon the values, or you want to use a percentage. So I selected like a linear percentage here. So once you define like shift low and high, so it will apply 5% from the exact, like if at a depth it's 2.2, 5% low side and the 5% low high side, the values are calculated, and within this user defined range the Monte Carlo uncertainty is run. So if you are like selecting a triangular distribution, for example, it is possible like if you generate a log uncertainty, which is multimin output, you will get a plus and minus curve. You can select that also. Also, if you use like a determine uncertainty, from there you will get plus the low and high value. That also you can use to define the range. So here I select like normal distribution, and I select for RW and the RW temperature. So, and I want to see the effect on effective porosity because I'm using an Indonesian equation. So I want to see for like effective saturation also. So once you define this, you can select how many iterations you want to run. You can run up to like 10,000. You can define also how many iterations to run. In order to generate a random value, you can put seed values if you want. So in this case, I select like just a default 250 as the iteration to save time. So once you select these things, you can hit the start button. It will show how the iterations is done. Anytime if you want to stop the iteration, it is possible to stop also. So it's, you can see like it's pretty fast. It is not taking much time, and even it's like a 250 iteration only. Once you run this iteration, we can view the result. So for example, if you look in this particular layout, you can see the porosity, effective porosity calculated, and you will be able to see the distribution of effective porosity. Same for the saturation curves and the distribution of saturation as an array curve. Once we have the array curve, it is possible to calculate the statistics. So statistics means I want to, from the array I want to calculate P10, P50 and P90. So you can use the array element statistics option in the Geolog general menu. I will restore the array statistic option. So you can see input and output set is the same. I've selected my effective saturation and I define like I want to know P10, P50 and P90 from this particular array curve. If I run it and if I go back to the model, so you can see in the last track P10, P50 and P90 values which I have computed. So what I show in this demo is like the first one was how to build like a simple multi-min models, how you can do the QC. So you can see how the volumes. So the volumes are the computed from multi-min. The porosity and saturation is a post-processing results from multi-min. So you can see the QC plot also. And then I talked about the model mixing. So if you have two models, you can mix the model based upon the proportion. So you can see the how the model mixing is happened at each depth. Even from multimin, it is possible to generate synthetic logs also. And this is good like if you are doing a rock physics analysis. So if you have a good multimin model, you can use the volumes even without like doing a rock physics model, you can generate a synthetic acoustic log also. Then I talked about uncertainty. So how to run Monte Carlo uncertainty to generate the uncertainty distribution for each of the logs. Coming to the presentation. So this optimizing petrophysics is very helpful to calculate reservoir properties in complex reservoir, both unconventional and unconventional. We can use this multi-min model to generate synthetic logs. Uncertainty analysis can be used to estimate overall uncertainty in the results. So the uncertainty analysis doesn't say which is right or wrong. You can understand the overall uncertainty in the results and you can identify which is the variable having greatest impact on the results.